This is a clip where some questions are asked to today's physicists. Of course, you're welcome to ask some and do so in the comment section. They may be included in a future clip. I am one of the physicists and probably do not completely agree with some of the answers. ChatGPT is among the many sources I have interacted with in the past. What is the interaction between energy and space-time, such that energy curves space-time? The physicist: this is unclear. ChatGPT beats around the bush. Einstein just, through tensor calculus, geometrized energy, without specifying the internal geometry of energy. He then compared it to geometrized space-time in an equation. This works quantitatively, but does not rest on some underlying machinery. It provides incomplete machinery with which gravity is communicated from place to place. It is a step up from Newton's gravity, where it is unclear how gravity is communicated from place to place. My response: there is no interaction between energy and space-time because energy is changing space. There is only changing space. It's a step up from Einstein's geometrized energy, in the sense that the energy now gets an internal geometric structure. It's only in the second layer of the human paradigm and perspective that this distinction between energy and space-time is made. Reality does not need this distinction and is dynamical enough on its different length scales to support the particle perspective as well as the cosmological perspective that humans have. Does Einstein's general relativity equation work so that dark matter can be added to the energy tensor? Or does the equation have to be modified because the metric tensor is more dynamic than we assume? The physicist: there are two camps. One says the equation is all right and dark matter just has to be found and added to the energy tensor. The other camp says we need either a modification or new physics, like modified Newtonian physics. My answer: just adding new stuff to the energy tensor is in my opinion misleading, but could work quantitatively. Conceptually, it's incorrect. In this second solution, where Einstein's equation is modified, the metric tensor is dependent on a new type of energy that has to be added, either in the shape of an additional metric tensor or as a new tensor added to the right of the equation, or as both. Mathematically, this is all the same, as is adding dark matter to the energy tensor. Conceptually, this new type of tensor should represent shaped dynamical C-space, different from the cosmological constant, being dark energy, and different from so-called dark matter that is supposed to be added to the regular energy tensor as some new particle. Dark energy isn't dynamical enough, if existing at all, and the word dark matter is misleading. This added tensor or tensors would be a fix of Einstein's equation that works, because we need to explain our human perspective. In any way, Einstein's equation is a mathematical tool. As a mathematical tool is quite sufficient to do the quantitative job, but just lacks a bit of conceptual machinery. In reality, there's only dynamic changing space, dynamic C-space. Particles are changing space. Human spacetime and the perspective of separated particles are inferred from changing space. Einstein just did not expect changing space to be so dynamical, and observations weren't very compelling at that time. They are more compelling today in the sense that a lot of other solutions are becoming unlikely. In neighborhoods like our solar system, Einstein's equation already suffices. The third option, where for instance Newtonian mechanics is modified, is in my opinion a step in the wrong direction. Why does dark matter just go on through other dark matter when the gases in two clusters of colliding galaxies collide? The physicist: this is not clear yet and under investigation. ChatGPT adds: dark matter interacts gravitationally with other matter, including itself and ordinary matter. However, it does not interact electromagnetically or via the strong or weak nuclear forces. Me: because the long wavelength waves of changing space, and as such of Einstein's spacetime, pass each other just like water waves. Spoken from a human perspective, the long wavelength waves of way more dynamic spacetime than anticipated pass each other just like water waves. The stars, made of way shorter wavelength changing space, do not collide on average because distances between them are much bigger than the stars themselves. Only the gases collide and mix. Again, this is the human perspective. In reality, it's just changing sea space, moving where waves of large wavelength move through each other easily, and the term superposition is better suited than the term collide. Are space and time in space-time on the same footing? The physicist: in the framework of space-time, as described by Einstein's theory of general relativity, space and time are treated on the same footing, forming a unified four-dimensional continuum. This concept was a revolutionary departure from classical physics, where space and time were considered separate and absolute entities. Me: from the perspective of an object in some surroundings, like a person or some measuring apparatus, we can create concepts like space and time and relate these. It now becomes necessary to join space and time into space-time because clocks behave the way they do and space-time contracts in the direction of movement. But clocks are geometric shapes that just move and change, and we infer a concept we call time from the seemingly regularity of the movement. Time is a paper concept to get some sort of grip on the physical phenomenon of change, of space and in space. Space and time are really different things. Space is all there is, and it can change and changes, giving the possibility of introducing a measure of change that English-speaking people call time. Space changes at a certain rate that seems constant. We associate this with the speed of light. Any sufficiently complex and therefore slower moving shapes in reality can perceive non-existing distinctions, such as local time and space impressions, according to special and general relativity, where space-time is a good mathematical and physics object.